In this video, we're going to have some fun talking about CMOS inverters. So I'm going to start by drawing the schematic for an inverter, and I'm just going to draw some generic MOS devices. One of them is going to have a connection to ground, and the other has a connection to VDD, which is the highest voltage in the circuit. And we know that the source of the PMOS device is higher than the drain of the PMOS device, so that means this is our PMOS device. And the source of the NMOS device is lower than the drain of the NMOS device. So this is our NMOS device on the bottom. And I'm drawing them the digital way, and what that means is that there's a bubble on the PMOS to indicate which one is the PMOS, and there's no bubble on the NMOS. Notice there's no arrows on the digital version of the NMOS and PMOS devices. So it just makes the drawing maybe a little more simple. We're going to label all the nodes in the circuit. The input is here. The output is here. Today when we're working with the inverter, we're going to connect the input to a voltage source that looks like a pulse. So this would be something like V pulse if you were working with PSpice, and the bottom of it's going to go to ground. Now what do we connect the output of the inverter to? Well, in real life, the output of this inverter is either going to drive another logic stage. So maybe it'll drive the input of another inverter or many inverters. So I'll draw the symbol real quick of the inverter, and it may be something like this where you would have one inverter driving several other inverters. Or this inverter could be sending the signal from the IC out into the real world. And the way it does that is by sending it to a pad first, and then this pad is connected to a package using a wire bond, and then that package goes onto a PCB, and that is connecting your IC to the outside world. Now either way, both of these situations, both the pad and the input to the next logic gates, can be modeled as a load capacitance. So we're going to connect the output of the inverter to a load capacitor, and we're going to call that CL. So the way we're going to think about this today is we're going to look at what happens to the output voltage of this circuit with respect to time. So I'm just trying to draw an arrow here. That shouldn't be that difficult. Okay, so this is going to be voltage on the y-axis and time on the x-axis. And first we're going to start with the input voltage. So the input voltage is a square wave. So it's going to start low, it'll stay low for a little bit, and then it's going to transition high, and it'll stay high for a little bit, and then it'll transition low again. And the first thing that I want to note here is that the square wave looks ideal. Now, what does an ideal square wave look like? Well, it just looks like from the time it takes to go from 0 to the highest value, and from the highest value down to 0, it can do that in a very short amount of time, basically infinitely fast. So what are the low and the high voltages for the circuit? Well, the low voltage is 0 volts, and we already talked about that the high voltage is VDD. And typically, I like to stay away from numbers and equations because I think when you're developing an intuition for the subject matter, it's kind of helpful just to sit and think about how it works instead of just leaning totally on the equations. But today I'm going to throw a few numbers at you just so you have an idea about the scale of things. So for a 180 nanometer process, this would be an old process, by the way, VDD would be equal to 1.8 volts. And the threshold voltage for the NMOS device, I'm going to call VTN, would be 0.4 volts. And the absolute value of the threshold voltage for the PMOS device would also be 0.4 volts. There's a couple things to think about here. For a PMOS device, the gate voltage needs to be lower than the source voltage by the threshold voltage. So the threshold voltage actually looks negative. So that's why we're just going to take the absolute value when we think about it. Now what we're going to do is we're going to try to relate what we talked about in the bias videos for the NMOS and PMOS device to what's happening here. So we're going to draw another set of curves, of course. All right, and this time we have ID versus VDS. And this will be for the NMOS device, so I'm just going to redraw these. These look something like this. This maximum VDS is going to be equal to VDD, and these are different values of the gate to source voltage. So we could call it VGS1, VGS2, and VGS3. And for example, VGS1 could be really close to the threshold voltage, so maybe this is like, half of a volt, and then maybe this is 1 volt, maybe this is 1.5 volts or something like that, just so you have a scale in your mind. So initially when we start out, we've got 0 volts applied to the gate of the NMOS and the gate of the PMOS device. So first we need to think about what is VGS for the NMOS device. Well, for the NMOS device, VGS is equal to Vin minus ground. So it's just equal to Vn. And for the PMOS device, sorry, let me annotate that. Okay, so for the PMOS device, what is VGS? Well, VGS is equal to Vn minus VDD. Now what we want to think about is at what VGS do the NMOS device and the PMOS devices turn on. So we're going to have a special name for that. We're going to call that VGSP on and VGSN on. And for VGSN on, this one's pretty easy, right? This is just Vn is bigger than the threshold voltage, VTN. Okay, for the PMOS device, it's actually pretty easy too, right? Because all we know is that Vn needs to be less than VDD by the threshold voltage. So Vn minus VDD needs to be less than VTP. Okay, so these are the points at which the PMOS device and the NMOS device turn on. Let's label those in this plot right here. So if VDD is 1.8, then maybe this is 0.9, and this is maybe-ish 0.4. Okay, so maybe this is VDD minus 0.4 volts. 1.4 volts. And so that's useful for us to think about those, right? Because now we have an idea in our brain that, okay, when I transition past this point, I'm turning on the NMOS device, and when I transition past this point, I'm turning off the PMOS device. So anything up here, the PMOS is off. And anything down here, the NMOS is off. Okay? I'm actually going to erase those because I don't want this to get too busy. I think it's already too busy. So initially, when the input voltage is 0, the gate to source voltage of the PMOS device is 0 minus VDD. So it's equal to minus VDD. That is the biggest possible value that it can be. So the PMOS device is on and the NMOS device is off. And remember, when the PMOS device is on, this looks like a closed switch. I have a short between VDD and the output. And so my output is going to be VDD. So it's going to be up here. Now it's going to stay up here until I get to this point in time. And at this point in time, my NMOS device is going to turn on and my PMOS device is going to turn off, because I told you this happens right away. So I just basically shoot right from 0 all the way up to VDD. So when that happens, what's going on? Well, now this switch right here is open, right? Because the PMOS device is off. Draw an arrow. I'm at this point in time right here. Kind of looks like an arrow. Okay. Well, the VGS of the NMOS is just equal to Vn, and Vn is equal to VDD. So I'd be somewhere on this curve. I'm at the maximum possible VGS. But now I want to know, what's the VDS of the NMOS device? Well, the VDS of the NMOS device is simply V out, right? VD is here, VS is here, so it's V out minus 0. VDS of the NMOS device is just equal to V out, and that is VDD. So we're actually at this point on the curve right here. So our NMOS device has the maximum possible current that it can sink going through it at that point in time. It has the maximum VGS, the maximum VDS, and the maximum ID. So since it has the maximum ID, it's going to be pulling the maximum current that it possibly can out of node V out. The output voltage is going to start to drop, and it's going to drop at a specific rate, and that rate has to do with how quickly a constant current source can discharge a capacitor. And we're going to move along this line right here as it discharges. Because remember, when I say discharges, that means VDS right here is getting smaller and smaller, which means we move towards x equals 0 until we get all the way down to right here and there's no more current flowing and VDS equals 0. And what that means is that the switch is closed, but there's no more current flowing. And because there's no current flowing, that means V out is equal to ground. And so that's this point right here. There's no current flowing and now I've pulled this output node all the way down to ground. So again, I'm just going to draw horizontal lines. So again, I'm going to draw a horizontal line, and now this time, because we're tracking the input voltage going from left to right, so now the input voltage is going to drop from VDD all the way down to ground, right? And so as the input voltage drops from VDD closer to ground, this point in time right here is when the PMOS device turns on. So everything below this point, the PMOS device is on. And everything below this point, the NMOS device is off. So as the input voltage drops, first my PMOS device starts to turn on, and then my NMOS device starts to turn off. So because my NMOS device turns off, I'm now able to charge up that node. And that node is going to charge all the way up to VDD, and it's going to charge at a rate that's going to be proportional to the constant current source of the PMOS device. So whatever this PMOS device, the maximum current in the PMOS device can handle, and it's going to be charging up this load capacitor. And again, we could draw the same curves for the PMOS device, and we could say, okay, what is VGS at this point right here for the PMOS device? So actually, let's think about that. So the VGS of the PMOS device at this point is going to be 0 minus VDD. So the VGS of the PMOS device is minus VDD. That is the maximum value for the gate to source voltage of the PMOS device. So it's going to have the maximum possible VGS. Well, at this point right here, the output voltage V out is 0. So let's look at VDS. VDS is going to be 0 minus VDD. The VDS of this MOSFET is minus VDD. So this PMOS device has the maximum VGS and the maximum VDS that it can possibly have. And it also has the maximum current it can have. So you could picture the PMOS curves. They would go in the other direction. I'll just draw them real quick, actually. They would go something like this. This is not to scale, but they'd go something like this, right? Just like the MOS devices. Okay, maybe this one is the max value, IDP max. Okay, so if this was minus VDD, and this was the minus VGS3 max, then we would be right here. We'd have a maximum current flowing through the PMOS device. That current is going to go from VDD to the output node, and it's going to charge up that output node. And as it charges up the output node, the VDS of the PMOS device drops, because the current going through the PMOS device is pulling V out closer and closer to VDD, and VDS is simply V out minus VDD. So VDS is dropping. We're moving along this curve right here, finally until we get to this point right here where there's no more current flowing and there's no difference between the source and the drain voltage. And all that means is that the PMOS device has completely charged up this node right here, and now V out is all the way equal to VDD, so we're somewhere right here maybe, and there's no difference between the source and the drain voltage. So hopefully this helps give a little bit of intuition about the inverter.